Today, we are cracking the code. We're going to pop the hood on that so-called black box of AI and really get into the nitty-gritty of how these incredible models that are changing our world actually, well, think. You know, it really does feel like magic, doesn't it? You snap a picture and boom, your phone knows exactly who's in it. Or you mumble something into a translator and out comes a perfect sentence in another language. Well, I promise you, it's not magic. It's all thanks to neural networks. And the core idea behind them is actually way more intuitive than you might think. So, here's the game plan. First, we'll look at the original inspiration, the brain's blueprint. Then, we'll dive into how a machine actually learns. After that, we'll explore the wild zoo of different AI architectures. And to wrap things up, we'll peek into the future, into what's being called the post-transformer era. Right, so the pioneers of AI started with a really fundamental question. Can we build a machine that learns the way a brain does? I mean, they looked at the only thinking machine they knew that worked for sure, our own, and decided to build a model inspired by it. The goal wasn't to create consciousness or anything, but just to copy the brain's amazing knack for learning from experience. And this is where it all started. On the left, you've got a real biological neuron. It gets signals, processes them, and decides whether to pass the message along. On the right, you see its artificial cousin. It's really just a simple piece of math that does the exact same job. It takes in some numbers, crunches them, and spits out a new number. It's a really elegant, really clever simplification of the real thing. So how does that math work? Well, every artificial neuron has two key settings, weights and biases. Just think of the weights like little volume knobs for each input. A high weight means that input is super important, while a low weight means the neuron barely listens to it. And the bias? That's kind of like a neuron's baseline enthusiasm. It's an offset that helps it decide to fire, even if the inputs aren't all that strong. These two things, weights and biases, are the only things the network actually learns. And what a neuron does is dead simple. It's just a three-step process, repeated over and over. First, it takes all its inputs, multiplies each one by its weight, and adds them all up. Step 2, it adds its own personal bias value to that total. And finally, step 3, it pushes that final number through something called an activation function, which makes the final call. Does it send a strong signal, a weak one, or just stay quiet? That's it. That's the entire job. Now, one of these little calculators on its own is honestly pretty useless. But the magic happens when you connect thousands or even millions of them together in layers. The output from the first layer becomes the input for the second, and so on. Suddenly, you get this incredible emergent complexity. The network as a whole can start to recognize patterns that are way, way too complex for any single neuron to ever see. Okay, so we've built this giant network, but when you first switch it on, all those weights and biases are just random numbers. It's a total blank slate. It knows nothing. So how do you take it from that state of complete ignorance to an expert that can tell the difference between a cat and a dog? Well, this is where the learning in machine learning really happens. The learning process is this beautiful, elegant feedback loop. First, the network makes a guess. We call this forward propagation. Then it checks the answer. It calculates exactly how wrong its guess was. We call this the error or the loss. Then comes the brilliant part. It works backward through the entire network to figure out which connections were most responsible for the mistake. That's backpropagation. And finally, it adjusts all those little weights and biases to be a little bit better next time. You just repeat this loop millions of times, and with every single cycle, the network gets just a tiny bit smarter. Let's focus on backpropagation for a second, because it's the absolute heart of the process. Think of it like a detective. After the network makes a bad guess, backpropagation is called in to investigate. It goes back through every single connection and calculates the precise amount of blame that each weight and bias gets for the final screw-up. It doesn't fix anything itself. It just produces this detailed report, a list of gradients that says, okay, here's exactly what we need to change to get this right. And that's where its partner, gradient descent, steps in. If backpropagation is the detective, gradient descent is the mechanic. It takes that blame report, those gradients, and it actually goes in and tunes the knobs. It nudges every single weight and bias just a tiny bit in the right direction to lower the error. These two algorithms, working together, are the engine that powers almost all modern deep learning. Now, that basic learning loop is incredibly powerful, but researchers figured out pretty fast that one size does not fit all. The way you arrange the neurons, the network's architecture, matters a lot. A network designed for simple spreadsheet data is going to be absolutely terrible at understanding a picture. This realization led to what's now like a whole zoo of different specialized architectures. Each one evolved to solve a very specific kind of problem. Let's start with images. See, a basic network would just take a picture and flatten it into one long, meaningless line of pixels. It would completely lose the fact that some pixels are next to each other. But with images, that spatial relationship is everything. That's the problem convolutional neural networks, or CNNs, were born to solve. They use these clever little filters that slide across the image, scanning for simple patterns like edges, corners, and colors. Then, deeper layers in the network combine those simple patterns into more complex things, like an eye, or a nose, or a whole face. But what about data where the order of things is the whole point? Like words in a sentence or notes in a song. CNNs and basic networks have zero memory of what they just saw. And that brings us to recurrent neural networks, or RNNs. These guys were built for sequences. They have this special feedback loop that lets them hold on to a little bit of memory. As they process each item in a sequence, they feed a part of their output back into their own input. This recurrent loop gives them a sense of context. What they're seeing now is influenced by what they saw just a moment ago.
RNNs were a great step, but they had a major weakness. They had to process everything one word at a time. This made them slow, and more importantly, it was really hard for them to connect a word at the very beginning of a long paragraph with a word at the very end. Then, in 2017, the transformer architecture arrived and just completely changed the game. It introduced this revolutionary idea called self-attention. Instead of looking at words one by one, it looks at the entire sentence all at once, and for each word, it decides which other words in the sentence are most important to understanding it. This ability to process in parallel is the key that unlocked modern LLMs like ChatGPT. So you can think of it like this. ANNs are your basic wrench for simple tabular data. CNNs are your specialized tools for anything visual. RNNs are for anything sequential, where you need memory. And transformers? They're the current state-of-the-art power tool for language, all thanks to that self-attention trick. Each one is a purpose-built solution for a particular kind of job. But here's the thing about AI. The state-of-the-art doesn't stay that way for long. This quote from a recent discussion really hits the nail on the head. The people building this stuff are already asking the next big question. What comes after the transformer? Is the revolution already over? And that question brings us right to the bleeding edge of AI research. Because as powerful as transformers are, they have their own set of problems. And as we push them to their absolute limits, we're starting to see the cracks, which is driving researchers to invent what comes next. And here's the transformer's Achilles heel. It's cost. That amazing self-attention mechanism that lets it look at everything at once comes at a steep price. It has what we call a quadratic cost. Now, that's just a fancy way of saying if you double the length of the text you're processing, the amount of computation required doesn't just double, it quadruples. This creates an insane bottleneck when you want to process really long things, like a whole book or a research paper. It just becomes prohibitively slow and expensive. And this is where the next big contender enters the ring: state space models, or SSMs. New architectures like Mamba are designed from the ground up to solve this exact problem. They completely replace that expensive attention mechanism with a new system that has a linear cost. So now, if you double the text length, you only double the work. This is a game changer. It means they can handle massively long sequences way, way faster and cheaper than any transformer could ever dream of. And the search for what's next doesn't stop there. Another really cool idea gaining ground is the mixture of experts model. The idea is, instead of using one gigantic, monolithic model for every single problem, you have a collection of smaller, specialized experts, and you only activate the few you need for any given task. It's a massive win for efficiency. And then you've got things like neurosymbolic AI, which is trying to merge the pattern-matching genius of neural networks with the clean, logical reasoning of old-school symbolic AI, hoping to make models that are more trustworthy and easier to understand. When you zoom out, you can see that the entire history of AI architectures is really just a story of creative problem solving. We started with a problem. How do we mimic a neuron? Then it was, how do we see? How do we remember? How do we understand context? And now it's, how do we do all of that, but efficiently at a massive scale? Each new architecture is just the next chapter in that story. And that leaves us with one final, pretty mind-bending thought to chew on. We've watched these systems go from just matching simple patterns to now starting to combine that ability with logic, with memory, with real-time adaptation. The next big breakthrough might not just be a faster or smarter AI, but an entirely different kind of artificial intelligence. And figuring out what that looks like, well, that's the question that's driving the whole field forward today.